Hello everyone, my name is Aleksandra Leśniewska and I am a PhD student at Adam Mickiewicz University in Poznań, Poland. Today I would like to present you my two recent works. The first part of this talk is going to be about dust production and the second about dust destruction in galaxies. So we know that the universe is a very dusty place. Dust in the universe can absorb and remit up to 30% of starlight in the infrared. That is why the formation of dust has become one of the most important topics in galaxy evolution. It is well known that there are two types of stellar sources that produce dust: AGB stars and supernovae. But this is not the end. There is something like non-stellar source, for example, grain growth in the interstellar medium. There are also very well-known theoretical dust yields. We know that one AGB star is able to produce up to 0.04 solar mass of dust, and one supernovae up to 1.3 solar mass of dust. Very famous supernova 1987A. In the case of this object, observers detected there up to 0.7 solar mass of dust. In general, it is around 0.5 solar mass of dust per one supernova. But talking about supernovae, it's very important to notice that they are not only dust producers, but they can also destroy sometimes most of their dust which they already formed by their reverse shock waves. So the question in my work was, what is the mechanism of dust production at redshift more than 6? In this work, we have selected all galaxies at redshift more than 6 up to 8.4, for which observations of dust continuum have been attempted. You can see in here 4 parameters: total dynamical mass, dust mass, gas mass, and stellar mass. Based on all of them, we were able to calculate the required amount of dust which one star, one supernova and one AGB star must produce in order to explain the total amount of dust in these galaxies. And this is the result. This plot shows us the dust yield per star as a function of redshift. It's also divided in 2 parts. The top is for supernovae and the bottom for AGB stars. You can also see these 3 regions, and they show us the limits. So in here is 0.3 solar mass of dust without 1.3 solar mass, which is without dust destruction. The dashed region, 90% of dust destruction by supernovae, and in the case of AGB stars, it is 0.04 solar mass. So these 3 limits. What can we say about our galaxies in here? So these 2, H-Atlas and SPT East region. For these galaxies, the required dust yield per star is about 0.1 up to 1 solar mass. This is close to the maximum dust yield predicted by simulations, as you can see, and to the highest observed values. Therefore, it is in principle possible that dust in these galaxies was formed by supernovae, but they must be that would require weak dust destruction and very efficient production. We cannot say the same, we cannot accept a similar conclusion for AGB stars, because one AGB star would need to create about 0.1 up to 1 solar mass of dust to explain the dust mass in these 2 galaxies, which is significantly higher than the allowed values. In the case of these three SPT West region, J1342 and A2744, it is possible that supernovae are responsible for dust, for observed dust. Even some dust destruction, but not a significant amount by supernovae would be allowed in these cases, as the derived dust yields are above 0.1 solar mass. For the remaining galaxies, let's say these three, Imiko, CR7 and SXDF. For these three, we have only information about upper limits for the mass of dust, so we cannot rule out either supernovae or AGB stars as dust produces. We can only conclude that one supernova in these galaxies could not produce more than 0.01 solar mass of dust. And last but not least, max. We also cannot rule out the dust production mechanism because of the large uncertainty on the measurement of its stellar mass result in the derived dust yield consistent with 0. So in summary, as you could see, AGB stars were not able to produce observed amount of dust. Supernovae must be maximally efficient and do not destroy actually any of dust which they already formed. And it suggests that there must be something else, some other mechanism, for example, non-stellar mechanism, which was responsible for observed dust mass. And the second part of my talk, dust destruction. As you could see, AGB stars and supernovae are stellar sources. But in the context of a high redshift universe, we can say that the interstellar medium and the grain growth in the interstellar medium is responsible for a significant amount of dust. The mechanism of dust removal in the universe has not been completely understood yet. However, dust evolution is not only relevant in the context of interstellar medium, but is also one of the main factors defining the evolution of stars and the entire host galaxy. So there are several processes that can contribute to dust loss. For example, astration, which is incorporation in newly formed stars, occurs regardless of the source of dust. The second, supernovae reverse shock waves, which I already mentioned in here. So supernovae are able to destroy a lot of their dust by reverse shock waves. The third process, another one, is ionization by planetary nebulae, where heating of matter caused by ejection can lead to the destruction of dust. And the last one in here is a galactic outflows contribute to getting rid of dust, and this process can be very efficient due to radiation pressure. We will address this issue by the analyzing of several thousand dusty galaxies which are becoming passive. They are elliptical galaxies, so we can say that they are early type galaxies. They are elliptical galaxies in which star formation has a much lower rate than what their masses could imply. Yet an unnaturally large amount of dust is observed, comparable of course to the amount of dust in spirals. Instruments such as the Herschel Space Observatory have only recently been able to provide deep infrared observations of hundreds of square degrees. Recent years have brought a large amount of new observational data containing information about dust emissions in low redshift galaxies. one of the major cosmological and galaxy evolution observation project is GAMMA. And all of my analysis will be based on this project. Up to now, dust emission of only several dozen of dusty galaxies becoming passive has been analyzed. As presented in here, this is a plot from a paper Michałowski from 2019. There is evidence of an exponential decrease in the dust mass with the mean stellar age for early type galaxies. This was based on only 60 early type galaxies observed by Herschel. The sample size did not allow studying the dependence of the dust decline as a function of other galaxy properties, prohibiting full understanding of this process. The approach to determine the rate of dust loss as a function of galaxy properties will be implemented in my project. So in this project, in my project, we will investigate the relationships between properties of 3000 of dusty galaxies becoming passive to understand the dust removal. So these are our specific research goals. The first one, of course, the most important, selection of a sample of galaxies for the analysis. Of course, elliptical galaxies detected by Herschel. The second point is an analysis of a sample of several thousand galaxies, study of various relationships between galaxy properties. Then we will try to estimate the dust removal timescale. Maybe the next step will be to compare it with to compare observational results with simulations, and at the end the result will be a description of the theory of dust destruction in elliptical galaxies. Our preliminary research is based on almost 3000 dusty galaxies, elliptical galaxies, and for these galaxies, this figure presents us dust to stellar ratio as a function of galaxy's age. And as from the previous paper, you can also see in here this decline in time. So as I said, our preliminary research is about almost about 3000 dusty elliptical galaxies. And what's next? We are going to divide the sample into narrow ranges of a given galaxy property, for example, dust mass, shape, or stellar mass. And then we are going to measure the timescale of the dust decline, and at the end compare the observations with the simulations. Thank you very much.